Welcome everyone to the Dgraph October community call. I'm Manish, the founder and CEO of Dgraph. Along with me is Daniel, the head of customer success. You want to say hi, Daniel?
Hey,
We have Tejas, the head of slash GraphQL, Dgraph Cloud Operations.
everyone.
And we have Pawan, senior software engineer in charge of the GraphQL team.
Hey everyone.
And along with us, we also have a special guest today, Daniel Posthuma from Martin.ai. He's a software engineer at Martin.ai, and he's done some incredible work replacing Redis with Ristretto, along with a storage solution behind Ristretto. And he's going to give us a presentation about what they were able to achieve with Ristretto. And for folks who are not familiar with Ristretto, it's a caching library that we wrote, the Dgraph Labs wrote to be used at Dgraph in Badger, and and it's becoming popular outside in the Go ecosystem as well. So the agenda for today is we first have half an hour for Daniel to go over his presentation, and then we'll give you product updates from the Dgraph team, and finally ending with a Q&A. And again, if you have questions, please go to this link, bit.ly/dgraph-call-3, which takes you to our discourse forum, and you can put your questions there. We will look at the questions there to ask Daniel and to the Dgraph team, and answer those. I don't think we have the questions enabled in Zoom, so you would have to go to the discourse link. So please go there to ask any questions. All right. So why don't we get started with Daniel? Daniel, welcome to the community call. Really excited to have you here.
Thank you so much for having me. Awesome. Here, let me present real quickly here. Great. Well, thank you everybody for coming. It is great to be here with you. Like Manish said, my name is Daniel. I'm a software engineer at Martin, and today we're going to talk a little bit about caching. I'm going to take you through some of the recent architecture changes that we've made with the very specific goal of drastically cutting our cloud hosting costs. I'll outline some of our decision-making processes for selecting the technologies in our stack, and show you how we validated those decisions through benchmarking, observability. And the goal here is that hopefully by sharing our experience, it may help you kind of identify the right off-the-shelf software to use in whatever solution that you are working on. And of course, we'll definitely chat a bit about Ristretto, and hopefully you'll be able to identify where it may play a part in whatever it is that you're working on. So let's go ahead and dive in. Like I said, I'm a software engineer at Martin. We're an ad tech startup in the real-time bidding space. I'll share a little bit more information about what we do in just a moment. But I split my time about 70-30 between writing code and infrastructure work. And we are huge fans of Go at Martin. Nearly all of the code for the bidding side of our platform is written in Go. And most of the work that I do on my own is in Go, C or C++. I am super interested in algorithmic trading, also known as algo trading online. Just starting to pick that up, and in my spare time, I hack on a research operating system called Plan 9 from Bell Labs. It's a pretty interesting operating system. Recommend checking it out. But when I'm not writing code, I, of course, love spending time with my family. We recently moved and finally have a backyard for the first time, which is great. So we've been definitely taking advantage of that in this time. So before I can actually tell you a bit more about Martin, I should probably describe the space that we're in, which is real-time bidding. If you aren't already aware, if you are ever reading content from a major publisher and you're not paying for it, it is paid for by advertising. So publishers like New York Times, CNN will partner with ad exchanges, which are also called supply-side platforms. to monetize the available advertising space on their site. And this is kind of generally abstracted as like the supply side. On the demand side, we have advertisers, and most advertisers definitely don't have the bandwidth to maintain sophisticated software solutions for programmatically bidding on these auctions. So an ad exchange is going to send out an auction. This isn't done manually, of course, although there are some cases where they'll form direct deals with an advertiser to directly fill ad spaces on their site. But generally, it's all done programmatically. It's the same case with platforms like Pandora, Spotify, Hulu, things like that. So if advertisers can't or probably aren't implementing this on their own, what they are doing is partnering with what are called demand-side platforms, or DSPs, which will execute their advertising campaigns programmatically and do it all for them based off of specifications that they decide on. One of the issues here is that there is like a huge gap in technical understanding between DSPs and advertisers. There've definitely been issues in the past where some DSPs will kind of hide behind some of the smoke and mirrors and just charge exorbitant fees for the work that they're doing, and it can make figuring out the quality of where those ads are placed fairly difficult. And that's where we come in. So at Martin, we're an ad tech startup, but we're really driven by this mission of bringing truth to advertising. We built our DSP with the goal of bringing transparency and ingenuity to a space where it's definitely lacking. In addition to, I guess, providing a more transparent fee structure, which is quite different than most of our competitors, we always seek to actually validate whether or not we're doing a good job. And one of the tools kind of in our tool belt for doing that are incremental lift studies. And I'll chat a little bit more about what those are in just a few. But in addition to making these studies available to people who use our platform, we also write bespoke bidding algorithms to kind of cater for a bunch of different goals that an advertiser may have in mind. So at a high level, this is generally what our architecture for our bidding platform looked like about 2 months ago. So here we have the device that you're accessing the site on. That might be your phone, laptop. In the case of video, it might be a set-top box or something like that. And typically these auctions are in process for about 100 milliseconds. And so the SSP or the exchange will send us, as one of the bidders that they use, a bid request. And the time that we actually have to return that response isn't static. It's actually provided to us in the bid request, and that the amount of time that we have can kind of range from about 100 milliseconds all the way down to 20 milliseconds. So our bidder has to be pretty fast. And so I guess the question might be like, what is it actually doing like in that time? Some of these things might be obvious, but of course, like what it's trying to do is actually find auctions that match a very particular specification. And that turns out to not be trivial at all. It requires a lot of data to be able to make those kinds of decisions. And there are a lot of safety guards in place. For one, we need to ensure that there's no ad fraud going on, that we're not getting a request from somebody who is impersonating the New York Times, but isn't, say, actually the New York Times. And we have to make sure that the kind of surrounding content for the ad makes sense with what the advertiser is looking for. This is generally known as brand safety. We don't want to have two completely different things next to each other that don't agree with one another. It's generally not good for helping make advertisers money. One of the other things that we check for is viewability. So we don't want to spend money on a particular ad opportunity if it's likely that the ad is like just below the fold so that nobody will actually see it. So there's all these sorts of things that we are checking for in real time, which require access to a lot of data. So all of these decisions are generally published via PubSub and received by various subscribers, most of them being in our analytics platform. And our analytics platform is made up of several different microservices, mostly all written in Java or Scala. And they all use a pretty cool library for Java called Vertex, which gives you kind of nice abstractions around message passing, managing events, and things like that. And the goal of this particular part of our platform is to provide live pre-aggregated data for very fast reporting, which is actually a pretty large competitive advantage for us. Most of our competitors will actually like email you reports after like several minutes, and you have to like download a CSV. But with how we have things architected, you're able to get responses back on our site within generally about 100 milliseconds. So this is also going to generate pretty large data sets used for machine learning pipelines. It's scraping a bunch of data from domains and pages to try to kind of categorize what kind of requests we might be getting, as well as allocating budget in our bidder. If we want to optimize towards multiple different dimensions at the same time, we actually need to be able to tie those relationships together in our data platform and provide those to our bidder in a way that it understands. And again, all of this data needs to be cached so that the bidder can have access to it very, very quickly. So what this looks like is that from the perspective of our bidder, we're getting around 200,000 requests per second. That's our steady state. It can vary a little bit depending on what traffic sets that we have active, but generally we're steady at around 200,000 requests per second. Our P99 latency for this service is 10 milliseconds running on 30 nodes. So it does have to be quite fast. And there's obviously a lot of outputs of this process. So we are handling about a gigabyte a day of PubSub payloads with just event notifications. And our analytics platform generates about 75 gigabytes per day of data that is either going to make its way to BigQuery, which we use for storing all of our raw data, or it's going to make its way to Postgres, which we use for reporting, and of course, ultimately to Redis, which we use in our bidding process. So I guess with some of this context, you can probably imagine that the Redis side of this equation is going to become a problem. Each of these Redis clusters in the two regions that we operate within are very expensive to maintain. Each of these clusters required a ton of nodes in order to run. And even with these cache sizes, we weren't able to actually store all of the data that we needed. And this was costing like tens of thousands of dollars a month to actually run these sized Redis clusters that support the kind of throughput that we were looking for. So about a month and a half ago, we started looking for a solution to some of these problems. And our first step was to abstract out our caching logic into its own service. So instead of having kind of custom logic for caching implemented in all of the various microservices that we have running, just have its own that handles all of that. And in order to support low latency from the perspective of the bidder, we designed Mcache so that it could be actually consumed as a library from in our bidder and exposed as a gRPC API to the other services that need to interact with our cache. So this service does need to be horizontally scalable. We can't be like manually adding nodes when we get a giant spike in traffic. And so this is where we started, but kind of like the first question that came up is like, what database should actually back this? Redis was definitely too expensive, but what other things are out there? And we had a variety of criteria for making this decision. We have obvious budgetary requirements for this, namely be significantly less expensive than Redis. Ideally, this would be a simple to maintain solution. We are not in the business of providing caching services, so we shouldn't be spending a majority of our time managing our cache. It should be easy to scale out, and it has to be pretty fast. So the P99 latency for database queries needed to be below 5 milliseconds at the most so that it doesn't affect the P99 latency of our bidder in any kind of dramatic way. It has to maintain about a 5 to 15 millisecond P99 latency. And it's got to be able to handle a lot of operations per second. So generally about 500,000 reads per second and 100,000 writes per second. That's not what we are at on a daily basis, but depending on what kind of load that we're under, it can definitely scale to that point. So our first iteration on this idea was kind of a typical setup of putting Redis in front of Postgres. This ultimately didn't work for a few different reasons. One being just the nature of our data. The most popular keys would end up being cached in Redis, so we would get very quick reads from Redis, but most of our data ended up not being cached. So we would get terrible tail latency from Postgres, causing P99 in latency in our bidder to spike to even over like a second. So this general property is described in what's known as Zipf's law. And so what you're seeing here is basically just a small sample of domains. These are ordered in descending order based off of the frequency with which that we actually see those domains. And Zipf's law basically says that given like a large sample of items, the frequency of finding like any particular item is inversely proportional to its rank in the frequency table. So I guess put simply, like if you wanted to find out like for a given item, like how frequently it might come up or what's our probability of finding it, it would have a frequency proportional to 1 over n, where the word in our, or say that the item in our rank is n. And as you can see here, I don't have like a full Zipfian distribution kind of plotted out here, but most all of our domains are kind of greatly spread out. We have a few domains that get the vast majority of our traffic, and then it pretty quickly trickles off from there. And so given these kinds of results, we kind of recognized that we could only actually cache a pretty small percentage of our data, but the data that would be cached would almost always be cached. So in looking at how we wanted to solve this problem, that was kind of a key learning from our previous experiment in terms of identifying a solution. So we definitely needed to cache some of this data, and we were talking earlier, my first step was like, I'm just going to write this myself. And so if you wanted to start doing this, you might start with something like this, where you have a mutex wrapping a map. So when you're trying to access that data from your map, you'll lock the mutex, and then using goes defer keyword, unlock that mutex when this function actually returns. And then here we're just returning the domain at the given key. And for set operations, you would basically do the same thing, except for instead of retrieving the value, you're going to set it in the map. This looks fine, but that's only fine if you're at pretty low concurrency. Like as soon as you're in an environment, like a highly concurrent environment like our bidder is in, this is going to fall flat on on its face. Like you're going to run into a lot of contention issues. A request will build up while it's waiting for the mutex to unlock. Latency skyrockets. This is not the situation that you want. But this is exactly where Ristretto comes in. So Ristretto is developed by Dgraph, and what Ristretto is a concurrency safe in-process cache for Go. So it's not an external caching service or something like Redis. This is something that you would consume as a library in your application. So for our use case, this is actually exactly what we were looking to do. And the nice thing about Ristretto is that there's not a lot of boilerplate. It's extremely easy to use, and we use it all over the place in our bidder and caching services. And the goal of using Ristretto here is to prevent rapidly repeating queries for the same popular data. While like our data doesn't actually neatly fit into like a Zipfian distribution, which is what Ristretto is designed around, it's still extremely useful for preventing us like going out all of the time to try to see like what kind of metadata is attached to, say, the NewYorkTimes.com domain. This fits pretty neatly into our kind of cache everything approach. So we use this in several different places, which I'll show you. So this is taken directly from the README for Ristretto. If you haven't used it, it is just delightful to use. It's not just because I'm here, but Ristretto is definitely one of my favorite libraries. If I ever get a chance to use it, and it fits the case, I definitely reach for Ristretto. So here we're defining a new cache, and Ristretto has several different parameters that you can mess with, but there's really only two that are super relevant. One is the number of counters. These are basically the counters that Ristretto manages for maintaining like what should be admitted, what should be evicted, and there's some kind of general principles for setting this number. Typically, you're looking for about 10x the number of items that you're trying to keep in your cache. And then the max cost is basically how eviction decisions are made. So this is going to be the total size of your cache. If you've got like 1,000 items and you get like 1,001 items, something's going to get evicted. This is what controls that. So after you instantiate your cache, actually using it is super simple. You've got simple set methods, get, and the ergonomics around this is very, very nice. And so in our application, this is not our exact code, but this is kind of a rough idea of how we use it. So we have a gRPC endpoint or method for getting the domain. And so the first thing that we'll do is try to get that value out of Ristretto. And if it's not there, or if it is found, we'll actually return it. And here we're actually storing, we use protobuf generated structs that actually have an embedded mutex in them. So we don't want to just like copy it over and put it into our cache. So we actually store the binary information, which is also definitely a bit more efficient. So if we find it, we'll just return it. Otherwise, we'll go out to the database, try to find it, and then cache the result if we find it. I'm obviously leaving out all kinds of error checking, nil checking, like all of that stuff, but I highly recommend giving it a try. So in our application, we do this kind of in two different places. One is from the perspective of the bidder. We're making these calls. We want to cache the result there. And then in Mcache, our caching abstraction will, of course, cache those database results as well. So Ristretto is one piece of this puzzle. The other was trying to figure out like what's actually going to back all of this data. Where is it going to be stored? It's definitely not a great practice to try to put all of that in Redis. And so if you haven't heard of Scylla or used Scylla before, Scylla DB is basically Cassandra implemented in C++. There are a ton of other optimizations included in Scylla, but the entire focus of this project is on raw performance. It's extremely resource efficient. There's a great talk, I forget his name now, but by the engineering lead at Comcast X1. They were able to actually scale down a 1,000 node Cassandra cluster down to 78 Scylla nodes. It's a really cool technology. I definitely recommend trying it. But Scylla and Cassandra are both NoSQL databases. So in our cases, we didn't need like ACID transactions. We basically just were completely fine with eventual consistency. We mainly needed reads and writes to be super fast. And that's what Scylla is great at. So once we kind of decided to go down this path, we needed to actually measure our results. We used a bunch of tools in order to do this. If you've never used K6, I definitely recommend taking a look. It essentially lets you write like JavaScript and just send any kind of whatever payloads that you define in JavaScript at ridiculously fast rates to your running service. We used NoSQL Bench and TLP Stress for stress testing and benchmarking Scylla itself to actually validate that it could handle the kind of load that we were looking for. And then we use Linkerd, Prometheus, Grafana, and Jaeger in our Kubernetes clusters to get great granularity on what's actually happening in our applications. Linkerd will surface, among other things, latency data and kind of tie together traces that end up in Prometheus and Grafana, where we can look through them and figure out like, why was this application taking so long, or what was going on with this query? These are great tools to have available. So the result of all of this was that Scylla was able to keep up fantastically well. Right now, it's receiving about 100,000 reads per second, with the P99 latency for reads at less than a millisecond. We've got about 10,000 writes per second, and it's handling writes at less than a millisecond P99. This is all running on 6 N1 standard 16 machines. So fairly minimal hardware for the kind of work that it's doing. There's some other optimizations in here, of course. We've got NVMe drives configured in RAID 0. There's a bunch of other things that Scylla recommends. On the Ristretto side, Ristretto's handling 200,000 requests per second. And like I mentioned before, like our data isn't super cache friendly. But what we found is that a hit ratio of 13% is actually higher than we were getting in Redis. And the data that's there is almost always there. So these are for our most popular items. And we have this set up in a kind of interesting way. We've got about 250 megabytes per bidder node allocated for Ristretto. I actually started working on a bit of the side project to use a Raft protocol with a library that HashiCorp put out to kind of tie these different things together so they could know what is actually in the cache. But ultimately, with our data set, this was excellent performance from our perspective. And what this allowed us to do is actually completely get rid of Redis. So, like I said, we store most of our raw data in BigQuery, Postgres, but neither of those have changed. But in this case, we're able to actually increase how much data we have access to when we're bidding at 4 terabytes as opposed to about 1. And Ristretto, as our cache, is ultimately handling about 10 gigabytes across all of our nodes. And so this is what our architecture ended up looking like. And thankfully, our P99 latency for our bidder is unchanged. However, our bill definitely has. We saved about 91%, not off of our total bill, but off of the related infrastructure by making this move. So if any of this is interesting to you, definitely check out our site at Martin.ai. And feel free to reach out to me on Twitter. Handle is at DanielJamesPost. So yeah, that's what I've got. Thank you both. Thank you all so much for listening. And I'm happy to take any questions you guys have.
Thanks a lot, Daniel. It was amazing talk. Really enjoyed the journey that you shared with Ristretto and ScalaDB. Is that the right way to say it, right? ScalaDB.
We have internal debates on this. It's actually, I think it's technically Scylla, right. But Scala is way more fun to say.
I don't see any questions here in the community call page. Team, do you guys have any questions for Daniel?
I think we have a special shout out from our audience, Doc Donahoe, who works at New York Times and also who was our guest speaker from last month community call. So they want to say thank you to Daniel for giving New York Times a shout out.
Always. I actually had even more New York Times content in here, but ultimately I had to get it down. Thanks, Doug. I actually saw his talk from the last meeting. It was great.
Awesome. And I think one question that I had was the hit ratio is around, you said 20% hit ratio or something. Is that about the right number that you guys were looking for, or how much does that save you?
Yeah, that is what we were looking for. Like I mentioned, like in our initial implementation of just putting Redis in front of Postgres, with our data set, it's like depending on what resources we're looking at, it's almost random. So if you have Redis put it in front of Postgres, what you end up having to do is just scale Redis to the size of Postgres to get the kind of hit ratios that you might want. So for this setup, somewhere between like 13 to 20% is excellent, especially given how much smaller our Ristretto caches are versus like the total size of our data set.
There's one question from Mike Hawks in the community. Mike is asking, how do you manage the infrastructure for your caching, in like dealing with machine failures, exception management, and dropouts, etc.?
Great question. So we provision everything with Terraform. Scylla in particular, we use Ansible to actually configure the machines themselves. So there's a bunch of different, it depends on what part of our infrastructure we're talking about. So we run most of our workloads in Kubernetes. So in that case, node failures, things like that, we've tested quite a bit, and we're able to recover automatically from those. We'll fail over to a different zone in the case of Kubernetes. In the case of Scylla, we have basically 3 nodes per region, 1 in each zone. So if we start failing over in one, if one zone goes out, we still have 2 others, and we can spin up another one. What we're kind of working on, and what the Scylla team is actually working on as well, is providing Scylla as a Kubernetes operator, so that we'd be able to get some of the same kind of like scaling and recovery benefits that Kubernetes provides. But at the moment, Scylla is slightly more manual than we would like. If we want to provision a new node, we have to do that automatically. But some of that is just because it's a new technology, so we may not have all of the automation around it set up that we might want.
Nish, I think you're muted.
Oops, sorry. Another question from Mike is, how do you manage European versus US traffic for compliance?
Oh, that's actually a good question. So right now we're US only. That is definitely a pain point that we are going to feel relatively soon. So Martin's still a pretty early stage startup. We've only been around for about 2.5 years at this point, and the US market has been enough for us at this point. But we do have plans to expand out to other markets early next year. So we're starting to put together some of the plans for that and what kind of compliance constraints we may have on our configuration. So I guess to answer your question, right now we don't have any. We're kind of blissfully unaware at the moment.
One question that I had was, I think I saw that in the Strato cache you set it to like, I think 1 gigabyte in your thing, but in your code, but it was around 10 gigabytes is what you are using overall Strato for. How much memory was being used by Redis? Because if Postgres is using a terabyte of data, then I guess Redis must be more because there's no compression.
Yeah, so it's been through several different stages. So when we had Redis, kind of the Redis plus Postgres implementation, we had Redis as a 10 gigabytes per region. And we were seeing about the same hit ratios that we are with Ristretto, operating 10 gigabytes in total overall. And obviously Ristretto being in process, none of those Ristretto processes know about the others. So we're very much relying on the fact that the popular items that we're going to see are always going to bubble up and end up getting cached. If we wanted to like really try to increase our cache hit ratio, I think we'd have to do a bit more networking to get these caches to be aware of one another, or figuring out some way to optimize our data model so that they would be a bit more cache friendly.
Got it. So basically in the previous architecture, Redis was also like 10 gigabytes of Redis cluster in front of Postgres. So actually, I'm slightly confused. So what did you actually save on? So Redis was 10 gigabytes, Redis 10 gigabytes. Was there some big saving there?
Yep. Yeah, that was almost all in Redis. I don't know that I'm able to share the total dollar amount. I haven't asked that, but I can say that it was pretty substantial. Moving from storing literally everything in memory to only storing the relevant data in memory was like a huge optimization. And so we needed a database that was able to provide really fast reads, even with that being the case. So Scylla definitely fit the bill, but we looked at Cassandra. We thought about MongoDB as well. There were several others in the ring, but like for us, Scylla itself had like definitely a lot of points that were really interesting. So we kind of gave it a try, and we're super surprised with how excellent the results were, that we decided to just stick with Scylla. So yeah, the savings was definitely pretty substantial.
Nice. Awesome. All right. Well, if there's no other questions, Well, thanks a lot, Daniel, for joining the call and for the amazing presentation. Again, I think as mentioning before, the moment we saw your tweet about this big change that you guys did, we were like, would be great to actually have a talk by you, and I'm glad that we were able to make it work. So thanks again, and
Thank you for having me.
thanks for joining the call.
Appreciate it.
Bye. All right. Now we can move on to some of the other agenda items that we have, which is some updates about the upcoming 2011 release of Dgraph, nicknamed Chala, the Chala. Let me share my screen and where is it? Right here. Okay. We have a whole bunch of stability improvements. Over to you, Daniel, to go over them.
Yep. Thanks, Manish. So as Manish sort of previewed last community call, he said, we are seeing like a lot of out of memory issues that people are reporting, and that one of the goals is that we want to make sure that Dgraph can run with no more than 32 gigabytes of RAM. So in 2011, we're seeing that being realized. So once that's released next month, you folks can definitely get to experience that. So I think the main thing that we've done here is that we are utilizing manual memory management. So Dgraph is written in Go, but we are using CGO to link in JEmalloc, and we're going to use that. From the user experience standpoint, you don't have to like install JEmalloc ahead of time in the release binaries. We're going to statically link this. So from the sort of operations point of view, it's all the same. You just still download the single Dgraph binary and you're up and running, whether that's in just the binary themselves, Docker, Kubernetes, etc. And if you take a look at, say, memory profiles, we're definitely relieving a lot of pressure from the Go garbage collector here. In-use memory for Go is lower, and we're using that. We're using memory with JEmalloc, so they're not shown in the profiles, but we have better control over that memory, so we can allocate and deallocate and so on and so forth, like without having to keep idle memory around. So you can release memory more quickly, and we see this avoiding these out of memory scenarios. And this memory usage improvements is across the board. So we did it in bulk loader, in just the general operations of Dgraph with Dgraph 0, Dgraph Alpha, and we also made some improvements in the response encoding time. So for folks who have like large query responses, we did improvements here in memory to make this faster as well. So less memory usage and also quicker response times. So that's the general story here. And another issue that folks had reported were, general things about of Raft being slow or they weren't able to maintain a quorum. That's what sort of the error message that was showing up in the logs. So we had made a bunch of changes in the Badger side of things, and actually for the write-ahead log itself, we sort of removed Badger from the equation, and which was the previous storage in, say, 2007, and moved to a simpler file and map based storage for Raft. So this improves all the efficiency for Raft proposals, which are basically the core to pretty much every operation in Dgraph, and you shouldn't see any tick misfire or unable to reach quorum issues in your logs.
We also made a whole bunch of changes in Badger itself. For example, the way we were doing value logs in Badger, we have changed it so that value log is no longer being used as a write ahead log. In fact, each mem table in Badger has its own write ahead log, which can quickly get deleted right after mem table gets flushed to the L0. Now, if you guys don't know this terminology, it's just I think the one thing to take away from this is that before this change, you could run into these out of disk issues with Badger because it was harder for us to reclaim space from value logs. But with these changes, it will be Badger disk usage will also be a lot more predictable because write ahead logs in Badger would get freed up very quickly, almost instantly after the data gets returned to disk. Other changes in Badger involve optimizations in how we do compactions. We picked up a bunch of sort of ideas from RocksDB about how they were doing compactions, and that has made our compactions much faster. And we also like added some of our own ideas around how to improve compaction. So overall, this change has made compactions much faster, which means we can write data at a faster speed. To Badger. And similarly, Stream framework, again, more memory, manual memory allocation using this in the Stream framework as well. So that means when we are moving data around between Dgraph instances or taking a snapshot and sending it over from leader to follower, the memory usage is a lot more predictable. So essentially, in a way, we were able to get the best of, I would say, C++, which is manual memory management and being able to allocate and deallocate lots of like short-lived objects in Go using these techniques. I'm writing a blog post about these techniques because I feel that a lot of Go systems which have memory pressure can benefit from these techniques that we have sort of devised here at Dgraph. So if you are a Go enthusiast, you might want to look for that blog post to come out. But yeah, really excited about the next release because all of the common issues that we hear from people around, hey, Dgraph is running out of memory, or we are seeing these quorum issues, our badge is running out of disk. All of those things would be completely resolved in the upcoming release. Anything else from this slide, Daniel? You're muted.
Yeah, thanks. Nope, we can continue with the next slide.
All right. And I think in this slide, we have something amazing to show you. So go ahead, Daniel.
Yeah, so these are just sort of memory charts with, Grafana panels from bootloader runs. And so on the left is 2007.2, which is our current latest release of Dgraph. And what we're doing here is we're bootloading like a pretty sizable data set. It's like maybe 1.4 billion NQuads that with indices sort of generates like 5 billion edges in Dgraph. So lots of data here that we're loading in bootloader. And this charts out the memory usage over time. So the green line is the Go in use memory, and the yellow line is the sort of RSS memory that's reported by Linux. So RSS memory is probably like the one that would you track from the operating system perspective about what can trigger out of memory kills. So these are on the same axes, both of these pictures. So at the top is 56 gigabytes. Again, the target for Dgraph is to make it run in 32 gigabytes or less. And you can see on the chart on the left that it just goes up over time. There's some stair steps from say 30 gigs to close to 35 gigs, and then there's another stair step to 42 gigs or so. Yep, and then it ultimately goes above a certain amount, and it actually triggered an out of memory kill. So this bootloader run didn't complete, and the way to complete it in 2007 is to have a machine, just spin up another machine that has more memory. And so you can have a pretty beefy machine to finish bootloader. And
even if it would still get finished, because sometimes we've heard machines which have 128 gigabytes of RAM and still get out of memory.
Right. So one takes long, and also you just don't complete.
Yeah.
So definitely, bootloader doesn't work for folks who don't have that sort of setup. With the same exact setup in 2011, you can see that one Go in use memory is pretty stable. It does go up and down, but it's relatively the same, and that's sort of realized from the J.E. Malik work we've done. And the yellow line, which is the process memory, stays well under 32 gigabytes and doesn't get out of memory killed. So, and what I've heard from folks that in the community that have tried out 2011 as well is that they've not only were able to run bootloader within their machines instead of getting out of memory kills, but bootloader was also much quicker. So folks were running bootloader with these large data sets again, maybe it took like 48 hours, and now it's taking like 20 hours. So definitely huge speed ups there.
Yeah. And I think what's happening with this green line over here is this is the Go memory in use. And what we're trying to do is we're trying to just decrease the usage of Go memory in all of the critical places. So over here you saw Go memory jump up to 28 gigabytes, but on this side, on the right hand side, it just does not go. It probably goes to like 9 gigabytes. But I think probably in the later changes we would also get rid of some of these peaks in Go memory usage. So the idea for us is, again, as Daniel mentioned, everything Dgraph should be running in 32 gigabytes of RAM. And if you have a 32 gigabyte RAM machine and it goes out of memory, let us know, because that means you've identified something that we haven't seen yet. We worked pretty extensively on all of these memory improvements in the last few months. So excited about the 2011 release, which would fix all of these. So if you still see something more, let us know. So yeah, I think a lot of memory improvements, performance improvements coming up in 2011. Along with that, we also have a bunch of features that the GraphQL team has written. So to give the update about GraphQL features, we have Pawan.
Hey everyone. So we have a bunch of features which have gone in and which are going to be part of the 2011 release. The first one is Lambda resolvers. This is something that we have been working on for quite a bit, and it's something that essentially, we have a lot of users who would like to use this, and it would essentially this would allow you to run custom JavaScript along with along with all the GraphQL code that you already have. So this is something that would also be demoed in the next slide by Tejas. Apart from that, we have union types. So union types is something which is part of the GraphQL spec, and we are not supporting it until now, but it is going to be part of 2011. Uh, and then we have essentially geospatial types. So these types are already part of DQL and the queries that you could do to basically see essentially to be able to store data like point, polygon, and multi-polygon, and to do queries around them. You'll be able to do this in the upcoming release. And we have support for auth on interfaces. So interfaces is something that we already supported, but essentially the support for auth was missing on interfaces. So that's going to come in. And Apart from that, we have support for a bunch of filters, like doing hash filters and a between filter and an in filter. So all these things have been requested by users. Like there are certain queries that you could not do before because of these filters lacking, which you'll be able to do. And like once you upgrade and once you post a new schema, you'll get all these filters out of the box automatically. And then another thing that's coming is that in Cascade now you can supply parameters. So you can do Cascade with parameters, which is quite useful if you have a case in which you essentially like in a GraphQL query, you have some children that are mandatory, whereas others are not. So in those cases, parameterized Cascade can be really helpful. One more thing that's coming is auth with JWK URL. So with this now, finally, you'll be able to use you'll be able to use or like auth with Firebase and some other providers, which use a JWK URL instead of like a verification key. So that is coming. And then you have essentially all like from now on, you would have Apollo tracing on the query results. So you can when you get the query results, you would also get you would get some information about tracing, which would be in the Apollo tracing format. So again, this is something that you can use, and you can probably send this data over to some other system which can give you more metrics over the queries and how they run over a period of time. The next thing that we're doing is queries to be able to do count. So count queries which allow you to do count of the root and also count of children. Again, this is something which was there in DQL but was missing in GraphQL, and is also like a heavily requested feature. So that's coming in. And then we have support for int64 scalar type and also like a bunch of other bug fixes.
Really exciting. I think the date, and we already have date time, right? Because that was the other thing that was being asked.
Yeah, that's
time.
already there in 2007.
And between is for the date time.
It works for date time. It also works for int, and it also works for a couple of other types, if I remember. Float also. Yeah.
Perfect. And I think, could you just like elaborate a bit more about the auth with JWK URL? This is not the Firebase.
It's not the Firebase auth directly, but essentially what happens in Firebase is that essentially Firebase would publish like a JWK URL from which we have to fetch the keys for decoding the JWT. So what we were supporting earlier was that we were just taking the key, static key in the auth config, but Firebase, because it publishes those keys and also changes those keys, so what we have to do is we have to go to the JWK URL and refresh the keys periodically. So this is a mechanism that Firebase uses for publishing the keys for doing authorization, and also some other providers like I think that like there are a couple of other providers which use a similar mechanism, which don't publish like a static key, but it's like a dynamic key which refreshes, and you have to kind of see when it expires, and then you have to refresh it again, and you have to use that for decoding the JWT. So now that we support this in a generic way, any provider which publishes the key over a JWK URL would be supported by us
I
for
see. So
doing
that means Firebase
authorization.
is supported plus other providers who are following the same system.
Yep. Yeah. Yeah. Yeah.
Perfect.
Yeah.
And I think not that Apollo tracing, we have it, but at the same time, we also have open sensors integration in Dgraph. So you get Apollo tracing is definitely useful if you have Apollo on top of it. But even if you don't have Apollo, the open sensors and Jaeger and other stuff, that should work out of the box with Dgraph, and that actually gives you a lot more information about how the query latency is and in which servers took how long and so on and so forth.
Yep.
Perfect. And I think one thing I forgot to mention in the previous slide about the some of the data stuff that we have done over here is that we have tested Dgraph with we ran like over a terabyte of data sizes during these testings. And this is the bulk loader, but we also did testing for live loading a terabyte of data in Dgraph and so on and so forth. And things are running really smooth with these improvements. All right. I think next up is this exciting thing about Lambda resolvers. I think the some of the context over there is that we people wanted to know how they can run custom logic that they write in /GraphQL or in Dgraph, and Lambda resolvers is our sort of like one of the big part of the equation, big part of the solution there. So over to you, Tejas.
Yep. Thanks for that, Manish. Thanks, Pawan. Yeah. So as Manish mentioned, I'm going to speak a little bit about the Lambda directive, which is being introduced in 2011 and will land in Slash probably sometime in the next few weeks. So why Lambda? So Dgraph 2007 introduced the custom directive. So with custom, you could either call out to a remote endpoint to resolve resolve a GraphQL field, or later in the release, and this is probably 2011, you can even write a little DQL snippet that would execute and fetch some data from your database. But what we were hearing from our community is they want to do much more powerful stuff. There's just some stuff that you could not express either as as custom DQL, and we didn't want to maintain a different server. So what we heard very strongly from the community is we want some way to write custom code and have kind of custom resolvers that do something special, right? So we wanted it to be as easy as just take this schema, and here I have a very simple schema. It's just type item and has 4 fields. It has ID, it has title again, which is all caps, and it has a HTML version. We wanted to make it as simple as just tagging these with at lambda, which tells Dgraph that these are lambda directives, right? And the code for this, we wanted to make this also very simple, have a very small learning curve so that anyone can easily implement the resolvers. So we came up with an interface which sort of looks like this. You'll just need to give us a small JavaScript snippet which says add GraphQL resolver, and in this case, item.capital title. And the way this works is it just takes your title and it says title.to uppercase. This is a very simple, very small, self-contained JavaScript snippet, and Dgraph and the associate and the companion Dgraph Lambda will be able to evaluate this and give you a GraphQL interface that implements this end to end. So before we go any further, a lot of people will ask why JavaScript. So to this, I'm referring to something which is known as Atwood's law, which basically from Jeff Atwood, who's behind many things, including Discourse, which we use a lot. He said any application that can be written in JavaScript will eventually be written in JavaScript. JavaScript is very popular, and it was also easy for us to get this up and running. So let me first give you a screen share and show you what this looks like. I'm going to just open up GraphQL Playground. So what I'm doing over here, it's a very simple GraphQL query. If you're familiar with Dgraph GraphQL, it should look very familiar to you. I'm doing an add item. I'm adding 3 items and under the title, but I'm querying back both the title and the capital title. Okay, so let me just run this. Yep, you can see that it's, let me move this. Yeah, so you can see that it's put this, you've got back the title, and you've also got back capital title. We have not specified capital title anywhere in the input. It's come from that code snippet that I've showed you earlier. So let's do something a little bit more complex, which I'll walk you through. Let's query the items back. I'm going to get the title, the capital title, and now something called HTML version. Okay, so let's look at that. You can see return the results, and I have this very complex HTML that's been generated over there. Even more interestingly, you can see that some of these, like this item, let me get the ID as well. ID. You can see that some of these actually have links across. For example, this item, which is ID 23, has a link to ID 24, which is the next item in this list. So how do we make this happen? So while we were trying to figure out how to do this, the real question came is, what runtime can we enable for users, right? We want to allow users to do things, but not do such complex things that it'll bring down our entire, our entire infrastructure. We can't let you read environment variables or something, for example. So we want to allow you access to network, to different libraries. We wanted to prevent file system access, give you async so that you can do network calls, fetch, and handle security. And so what we came up with is, and this is something that's been done by other sort of serverless providers, which is we wanted to make an API which is sort of similar to Service Worker. So if you're familiar to all the APIs that you have in Service Worker, such as fetch, then you should be able to write a Lambda resolver very, very easily. Okay, so let's take a look at the code pretty quickly. It's not a lot of code, right? So this is okay. So sorry, this is the So this is the actual code. You can see the first one is exactly as I mentioned it. You can just say item.title. Let's look at something more complex. Because this is actually running in an environment similar to Service Worker, you can actually use Webpack to pull in any JavaScript library that's available on NPM. And you can use that with Dgraph, as long as it's all been bundled by Webpack into a single executable file. So over here, what I'm actually doing is I'm importing React. And I'm adding a resolver for this HTML version, which is this. So in this, just to be a little bit more fancy, the first thing I'm doing is I'm running a DQL query. So over here, I'm saying, give me all the Dgraph entities of item type and just give me the count of that. And then from that, what I'm doing is I'm calling a React function where I'm actually rendering a React component over here in my resolver itself. And that does some funky stuff like looking at all the items and then, having a link to the previous item, which is index -1, next item. And, I'm using your count somewhere. Yeah, where total. Yeah, I'm using the total for the count. So you can see you can do some pretty fancy things over here. We gave this second version of this so because you want to fire the DQL query once instead of firing the DQL query on every single item. You want to batch that into one single DQL query, which is shared across all those items. So and you can see it's actually very little code to do something pretty magical. Yep. So just last thing, this is already hit Dgraph master. Both the code for this is of course open source and it's in the community edition of Dgraph. There's also a Lambda Docker image that we're publishing, which I can send the link over. I think the link is mentioned somewhere. And this is coming in 2011, and it should be in Slash in a few weeks. So it's something that we've all been very excited for. And yeah, I'm actually out of time. We're exactly on the dot.
This is incredible. There's a few questions over here. So if you go back to a couple of slides before this, to the code that you had.
The actual code, yeah, sure.
Yeah. Can you just talk quickly about the add GraphQL resolvers and add multi-parent GraphQL resolvers? So is the first one, does it have to be the add GraphQL resolvers, and after that everything could be multi-parent?
Right. Okay. So like I mentioned, when you're actually firing the query, I think this is the actual query. You fire query item, and each one gets it queries each item one at a time. So that's over here. You want to choose between: do you want your function to be called once per item, or do you want your function to be called once overall, so that you can do some sort of performance enhancement, and then maybe share some results across all the items. So that's why in my example, something like just making a title uppercase, that can just be called once per function. It's very simple. It's it doesn't use anything. So that's why this function accepts a single parent, and it just does title to uppercase. This one accepts a group of parents. So that's why you can see it has multiple parents and fires a single DQL query and returns the results. Dot map is basically, take each parent and this is the result for each individual parent. So it's just a performance optimization if you want to do something a little bit more fancy.
So this is avoiding the n+1 problem, so that so we are able to batch a bunch of objects together before making that call to the Lambda function.
Exactly, yes.
Perfect. And how would you upload this code into Slash?
So that UI is something that I can actually show you in which should be there at least by the next community call. But what you'll be able to do is you'll be able to bundle your JavaScript together, and you'll have a nice button which says upload your Lambda.
And if like, do we have a system around how would they debug this in case there is something wrong with JavaScript? Like how do they iterate and all that stuff?
Yes, we are sort of working on some of these things, like how we export logs back to you so that you can actually see the things that are going on. Like a few of these things are in the pipeline.
Perfect. Yeah, this is extremely exciting. I think this is we have I think as I just mentioned, we have a bunch of different ways by which you can do sort of custom logic execution. One is the add custom directive, which is, I think add custom allows you to like put a DQL query so that you can bring the power of DQL to standard GraphQL. And this goes beyond what DQL can do as well. For example, DQL cannot convert to uppercase, cannot make you like run JavaScript code. And so this actually like kind of allows you to run your entire like custom logic within /GraphQL. So you don't have to build a separate backend, and you avoid all the layers that would come with having separate backends. So this is definitely very exciting. Let me see if there's any questions from the community. There's one question which says, regarding the parameterized cascade, will this address some of the outstanding issues with pagination and cascade over filters?
It's not going to address the issues with pagination. That's a separate bug that we have, which we're going to look into, and it will probably be part of the next patch release that happens. So I'm actually aware of the issue, but it's a separate issue which is pre-existing in Cascade, but we'll be looking into fixing that.
Got it. Another question is, things like auth on GraphQL, are these enterprise only?
Nope. It's all open source. So like auth on GraphQL is all open source. You don't need to use the enterprise version for that.
And we have a comment from Sean that that they have been running the new Dgraph, the Dgraph for master and seeing much less memory usage. So they are excited about that. All right, I think that probably covers all the questions that we have. Am I missing anything else, Zeni?
I think that's all the questions.
Perfect. We do. I think Terry Leach, he or she, they said wow. So well, that's probably for you, Tejas, for your presentation with the Lambda functions.
Yeah, I mean, the team's been working very, very hard on this one. Yeah.
All right. So all exciting stuff. One more thing is that the 2011 release, it would probably be running in Slash it would come in Slash before it would get released publicly. So if you want to get the new release, I think we'll definitely like update when it comes to Slash. We would be able to you'll be able to see all the improvements before it gets publicly released via GitHub. So one more reason to go check out Slash. And with that, I think we're slightly over time. Maybe we conclude here. Any parting comments, guys? Nope. Okay. Well, let's looking forward to to what people do with the next release of Dgraph. And thanks a lot for everyone for joining this community call. And we'll see you next month. Thanks.
Thank you, Manish.
Thanks, folks.
Thank you, everyone.